All right, guys. So we have talked about exponential functions and kind of how to write the equations, how to recognize the different things about different scenarios, the initial amount, is it growing, is it decaying, how to move and create the function by changing the percentage over to a decimal, or how to recognize from a function what the growth rate was or the decay rate was. We even looked at some tables and some graphs to try and pull some information off of those um, to create an equation. And we are going to go over a little different approach to that later in the week. But today I want to talk about graphs specifically. And so we're going to look at exponential graphical behavior. Okay, so that we can describe the movement of an exponential function on a graph. Okay, now we've done graphical behaviors before, so you're going to see as we kind of list out the things to note that we really do know a lot already. Okay, and so there are four major things that we want to note. Okay, four things to note uh, about a exponential graph or any graph really, but um, specifically exponentials today. Okay, so the first is going to be our domain. Okay, and if you recall, the domain is the possible x values. Okay. So all the possible x values on a graph, or that the line on the graph is going to cover. So if you could, right, you could go left and right. You would talk about all of those values. Well, if we're going to talk about the domains, we also need to talk about, right, the range, which is, right, the possible y's. Okay, so possible y values. That's going to be important, right? We can talk about the behavior of the exponential function as it pertains to the different y values. Something else to note, right? We've already kind of done this in trying to get a function equation from a graph. You want to really look at that y-intercept. He's important. He does a lot for you in terms of creating the equation. And then the new one for us today, right? This guy right here, he's new. We're going to talk about what's called an asymptote. All right. The asymptote is going to be what we're really discussing and exploring today, right? Now, I will kind of give you this ahead of time. These two guys, the range and the asymptote, are very closely linked. Okay. They will have a very big impact on each other. So you want to make sure, right, that they kind of work together. When you state one, you don't want it to conflict with the other one. All right. Um, they should work together. They should play off of each other, and they should, um, lead us into um, making the same kind of rule for both of them, right? You can't have one that says one thing and then the range is something else. You kind of got to play hand in hand. So we're going to explore this here in a second, and you're going to kind of see what I'm talking about. All right. So we're going to do it through an example, just so that we have something to look off of and something to think about. Okay. And so we're going to think about Brian and his starting salary and how it grows over time. Now, Brian starts at a salary of $5 a day, but gets a raise, daily raise, right? Daily raise of, right, 4%. Okay. And this all started on, we can just go with that, right? So again, this is super simple, super basic, but just so that we can get terms of thinking about like starting points and how they're reflected on the graph and linking those things together. So as we know already, right, we have our basic parent function, right? F of x equals a times b to the x, right? Where f of x is just y. So we can write these things in as necessary. So f of x equals, we have $5 as our initial value, right? That's our beginning salary. And then we have a raise of 4%, which is going to be, right? Raise, I get to thinking about, right? 1 plus my percentage, right? 1 plus the percent, whatever it is. But we want to use the decimal version, right? So I've got I want to make that 40%, just so that we get better movement out of the graph. 4% is not going to move very much day to day on a $5 starter. All right. So we've got 1.4 because 40% as a decimal is 0.4. And so we have our function, okay? So we have 5 times 1.4 to the x, which x is going to be determined by whatever our day is, right? So on day 1, day 2, day 3, etc. Okay, so again, this is doesn't have to be super accurate because we're just describing behavior. And so I'm going to draw a graph, and you can see my focus is in quadrant 1 here. Of course, there is behavior that happens not down here, right? If you're foreshadowing the movement of the graph, but we could work backwards as if this was some other scenario, and so there will be behavior this way. All right. Um, so how does Brian's salary stack up, or his daily rate stack up? Well, let's make a table of values of x's and so inputs and outputs, right? And again, remember f of x is just like our y. So as we make these different input outputs, we're talking about ordered pairs. We're talking about coordinates. Okay. So x at 0, right? Meaning 0 day, right? Before any time has passed. All right. What is the initial value? Well, it's 5, right? Because we put 0 right here. So 5 times 1.4 to the 0 power. Well, anything to the 0 power is 1. So 5 times 1, right? Then we start to build our table. Let's just use 1, 2, 3, 4, 5 to see if we can get some movement out of it. Now, I'm going to go ahead and switch over to Desmos and just kind of show you how I would be entering this. Now, you can be using a different calculator, and that's fine. You should have the Inspire. I don't have one handy at the moment, so we're going to use Desmos, and it kind of works the same as far as how we would enter it. So I'm going to put 5, and I'm going to multiply that by, right, and I'm going to put 1.4 in parentheses and close those parentheses, and I'm going to hit this button here so that I can just start plugging in, right? So 5.4 to the first power, or 1.4 to the first power, that'd be 5 times 1.4, which is 7, okay? And then I'm going to back it up, and I'm going to put 2, and that's 9.8, okay? And then I'm going to back it up, I'm going to put 3, apologize, okay? And that's 13.7, and I'm back it up and put 4, and that's 19.2. And again, we're not trying to be super accurate here, but there's 5, there's 26.9, and we can that's about as far as we took our table. So stopping that, and we're going to jump back onto so I have all of those values written out, right? These are all just ordered pairs off my graph. All right. So let's see, let's go. Right, let's just do this by, we'll do it by tens, 10, 20, 30, 40, 50. Okay, so that gives me a graph to work off of. So 1, 2, 3, 4, 5, 6, 7, 8. Right, 1, 2, 3, 4. Well, that's 4, not a 5, 6, 7, 8. And I can just plot my points, right? So 0, 5, that's going to be about right there. Okay. And then 1, 7, somewhere a little higher, right? And then 2, 9.8, a little bit higher, even still, almost 10. 3 is 13.7. So we can kind of start to see that upwards movement. 4 is now 19.2. And then 5, 26.9. So here, let's just go ahead and go to 8. So we can get an idea. So 6 is 37.6. 7, 52.7. And then 8, right? On the 8th day, he rested. No, I'm just kidding. So 73.8. All right. Okay. So I just went ahead and went all the way right through and calculated through 8 so we could get an idea of the movement here. So looking at 6 is 37.6. So we'll go up to that one, 37.6, 52.7 for the 7. So we're already up to somewhere in this area. 8 is going to be way off this graph. So if that's 60, that's 70, 73, and 8. So it's about right there, right? So you can kind of see how this graph moves, right? We've got a exponential curve, and I missed that completely. But that's okay, right? We're just talking about the movement, so ignoring that line. All right, so here we go, right? There we go. We have something happening here, right? We have kind of movement on this graph, and we can describe that, okay? So we have 4 things to describe. That is the domain, the range, the y-intercept, and the asymptote. All right, okay? Domain, range, asymptote. All right, so let's talk about these different things, right? Well, the domain is just all the x values that can exist on this graph. Now, it depends on the scenario, but typically, right, if we're just looking at the graph of any exponential function, it can move, right, as far left and as far right as we need it to, right? So we can do calculations for -1, and it has a value. We can do -2, and it has a value, -3, and it has a value. So these things, right, are going to have movement. And so there is movement infinitely to the left, and there's movement infinitely to the right because, right, we're just counting up in days. Now, in this scenario, right, we can't go backwards in time. So that might limit the domain that we talk about. So you have to be very careful, right? Domain is going to be considered, right? If there are no restrictions, no restriction. We're talking about just a basic exponential graph. There's not a real life scenario to go with it. There's no restriction. It can go from negative infinity to positive infinity. Okay. Because right there's nothing stopping it from moving left as far as I need it to. There's nothing stopping it going to the right as far as I need it to. But right then you have the real life. Okay. Real life just means that there's going to be things about the x value that I have to consider. That means I can't, right? I can't go backwards in time. In which case, right, this one would have a restricted domain. Okay, so we would have to start at 0. There's no going past that. It's a hard stop there. And so you really need to consider, right? What are they talking about? What's the domain here? Is it just a basic exponential? Did they just give me the function and no real life scenario to go with it? And in which case, right, we'd be talking about all real numbers, okay, with no restriction. If it's a real life example, right, now we have kind of this restricted domain because I can't go backwards in time. I've got to start wherever things started at and build from there. Okay, so just kind of taking what we knew about domain and range and taking it a little step further in restrictions. Okay, also, okay, let's talk about range. Kind of the same scenario, but in this case, we're gonna skip that one for a second because we really need to talk about asymptotes before we can develop a range. Um, so y-intercept, super easy, doesn't matter, real life or no restriction. Your y-intercept is what it is, and that is just a point on the graph, uh, and it's always going to be right your initial starting point, just as it was before. Right, there's no change, no restriction there. It is what it is. Okay, so let's talk about asymptotes and range. Okay. Um, and so I'm going to come back to this. I'm going to switch over to the next page here so I can write about asymptotes, describe them, and how they're going to apply to our exponential functions. Okay, so asymptote. Okay. Um, there are many very mathematical, academic ways to define what an asymptote is. But what I always kind of envision it as it's a invisible wall, okay, that a line can't cross. Okay, it's just an invisible wall that a line can't cross. Okay, so um, it's just kind of where things get. And so if you think about different graphs, right? Um, you have restrictions in where they can move to. Asymptotes can be horizontal, which means that it is a line with the equation y equals some number. Okay. Um, Horizontal asymptotes, right, are y equals equations. They move, right, like that. Okay. That's a horizontal asymptote, right? It's not restricted to a graph. We're not really looking at it. We're just thinking about what an asymptote is. It's an imaginary line, imaginary wall that the line can't get across. It can't ever actually get to it. It just kind of gets near it and then rides it. Okay. Now you also have vertical. Okay. Now, and we'll get to this. Okay. You have vertical. Okay. Is a line with the equation x equals a number, right? So if you need a vertical line, you're going to need an x equals equation, and that's going to create, right, a vertical asymptote, right? And so you have these in different scenarios in mathematics. You have what's called asymptotes, and they're just imaginary lines that you cannot cross, okay? Um, Exponentials, okay, we'll have horizontal asymptotes only. Okay, we are not, okay, ever going to be talking about vertical asymptotes in this unit. Um, I need to introduce them. You need to know, right? But we're never looking at an x equals equation because that creates a vertical asymptote. And at this time, we don't have those. Okay. We don't have those because that, again, recall, is a line that you cannot cross, you cannot touch. It's an invisible little force field that exists that turns the graph away. Okay, so we're definitely focused right here, horizontal asymptotes. Okay, so we can go back to our scenario and we can see like where is our asymptote? Because there is an asymptote. There's always an asymptote in an exponential function. There's always this point you cannot get past. Okay, um, and it just depends on, right, the situation as to where your asymptote's going to be, that you cannot touch, right? So going back to our scenario here, right? Going back to the previous graph and thinking about like the behavior. So obviously, right, we don't have one as we go up because, right, on the 9th day, we go up even further. On the 10th day, we go up even further. So we're going to keep moving to the right, which is why the domain is unrestricted on the increasing end, right? So increasing end, it's unrestricted because we can keep moving right as far as we want to, right? There's no ceiling here. It's going to keep going up, keep growing and growing and growing and growing. Okay, so we're going up, 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 up. Okay, now the question becomes like, if we're moving to the left, right, do we keep going down, down, down? And at what point do we stop? And so we have to understand what the behavior is, right? As we get lower and lower in value, what happens? Okay, is there a point of no return? Do we actually ever reach some value and stop dropping? Okay, so exploring the asymptote, we're going to look at what happens, right, when we go the other way on the graph. This is just kind of my asymptotic exploration. So I'm going to go with -1, -2, and then I'm going to go with -100. Okay. And these are just negative exponents. If you think back to the previous unit, that's basically going to turn my 1.4 into its reciprocal. And so you would have 1 and 4/10. So in essence, 14/10. You'd be turning that into 10/14. And then, you continue to do that as you need it. So exploring this from a calculator standpoint, right, we're just going to use the negative version. So -1, that creates 3.6. And again, I'm just kind of rounding it off. -2 creates a 2.6. And then -100 creates a, well, let's go. Yeah, that's fine. Okay. You get this number, okay, 1.2 times 10 to the -14th. All right. Okay, so those are our three numbers, and so you can see it's going down, right? As we go down, and that's what the graph shows us, right? At 1, it gets lower. At 2, it gets even lower. We could have done at 3, and it would have gotten even lower. But real quick, we can explore, what does this mean, right? So let's look at the backside, right? And let's talk about scientific notation. So we had 1.2 times 10 to the -14th. And what I've got here is simply a movement of 14 decimal places to the left from where it is. So this number, right, is really 1.2, and we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So there we go, right? There it is. All of these spaces get a 0. Okay, so you can see how very, very small that number is. That number is incredibly small. so small that we can't even imagine how small that is. And yet, um, it's still not zero, right? It is so small that we wouldn't even scientifically probably consider it, but mathematically, it is still not zero. And so, going back to our example, right? No matter how far we go out with this line, okay, it might look like it's flattening out, but it doesn't, right? It is just getting closer and closer and closer and closer to that um, x axis, but never actually going to touch it. Okay. So when we talk about an asymptote here, what we're talking about is the imaginary line, if we were to draw one, that this graph will never touch. And in this case, right, it is going to be y equals 0, okay? Because that is, right, this axis right here, this x-axis, it's never going to be able to touch it. It's going to get really close, right? So close that it looks like it's touching it, but it never really is, okay? And so the asymptote then defines the range. So we're going to get to 0 and go up. Okay. We can't actually touch 0, so it's a soft stop. We never actually get there, but that's where I would start describing it. So 0 and up. Same thing here, right? Our range in real life, though, okay, starts at 5, right? We can't go back in time. So this side of the graph doesn't actually exist. We start from where our scenario starts from, and then we start growing from there. So our range here, we can actually be at 5, and we go up from there. Now, you might say, well, the asymptote here would not be, well, since we can actually touch 5, our asymptote can't be at y equals 5. And so these two are linked here in a non-restricted environment, where these two really just depend on the scenario. So you really wouldn't describe an asymptote for a real world scenario because, right, I can touch 5, I can be at 5, and so my asymptote is not y equals 5. It would be as close to 5, right? So you would have to say, it is y equals less than 5 would be a more accurate asymptote, but that's not linear, right? This is not a line. And so, you kind of get a question there and you start to think about, like, am I really describing a line? Am I describing an inequality? So there's this region then that we cannot be in. We can't be anything less than 5. Which is what our range is describing. So really neither one of these kind of describe an asymptote for a real life scenario, but definitely unrestricted, we find that value for which we can never touch. Okay. I'm going to explore this a little bit more in the future just to make sure we've got a good grasp on it. We'll find some good example questions, and I'll put that out there for a PDF for you guys to review and work along with me. And so we can talk about real life scenario and how we develop kind of the range and asymptote from those things. All right. Any comments, questions, or concerns, just shoot me a message and I'll see if I can't get back with you as quick as I can. Thanks, guys.